Now we will move away from solving equalities and we will look at counts, because remember that we also looked at counts before understanding the nature of polyhedra and solving constraint for rational numbers. Here we will not go all the way to connect the full understanding of integer polyhedrons and how to reason about them. We will just introduce the Hilbert basis, which is a very important concept, and prove its uniqueness. So what is a Hilbert basis? If you give you a finite set of vectors a1 to am, you call it Hilbert basis if each integral vector b in the cone generated by a1 to am. The cone is not generated by integral combination. You can just take any non-negative linear combination of these vectors and you get a cone, right? And if all the integers appears in them are integral multiple, then we will say it's a Hilbert basis. So for example, let's suppose we choose a vector 2 2. Yeah, so it's a 2 2 vector. It's going to start from origin, it goes to 2, right? It's not a Hilbert basis because it cannot represent 1 1. 1 1 is in this cone, but 1 1 is not integral combination of 2 2. But 1 1 can be your Hilbert basis. Similarly, you can check out that various different pair of vectors in two-dimensional space are Hilbert basis or not. Each cone C is generated by an integral Hilbert basis. So there must be some Hilbert basis out there which can generate each cone. So that's how to prove that. So let b1 to bn be the set of integral vectors that generate cone. If let's suppose the cone is you have a set of vectors which do not integral, and they generate the cone, you just multiply them with certain constants so that all the entries in each of the vector become integral, and then you say okay, it's integral. So what do? We let a1 to at be all the integral vectors in this space, which is basically all the linear combination, non-negative linear combination of b1 to bm, such that the coefficient of each combination is less than equal to 1, and you collect all the integral vectors from this space. For example, let's suppose we have these two vectors which are integral vectors, and they were somehow spanning this whole cone. Okay, now what do? I want to collect a1 to at. Okay, so what are the a1 to at's? Just these two vectors, draw the parallelogram, all the integral vectors that occur in this parallelogram, you collect them. This becomes your at's. Okay? And we'll show that these at's are our Hilbert basis. So by first of all, b1 to bm are within this a1 to a. Now you take some integral vector c, okay, and therefore c is a some linear combination of lambda 1 to lambda m, and these may not be your integral linear combination. There must be some linear combination of vectors b1 to bm. What do? You take a floor. You take a floor of these coefficients and write it down like this, and then look at the other part, which is a fractional part, which multiplying with b1, and the fractional part multiplying with b1. These things are less than 1, okay, less than equal to 1, actually strictly less than 1, and they must be, should be an integer, okay, integral, because these are all integral and these are multiplied with integral, so the result is also integral. So this is integral, and our c is also integral, so this must be an integral. Therefore this guy must be in a1 to at. You must be inside a1 to, one of the elements a1 to at must be here. Yeah, so you can see that the c is a non-negative integral combination of a1 to at. Okay. Now you can say further, if it is a pointed cone, means that the cone just look like pointy like this, not full dimensional space. In two-dimensional space, you can just whole space can be viewed as one giant cone, and we say, well, not like that. Only when there's a pointed cones, then there is a unique Hilbert basis for C. Let's say, how do you prove it? We define what is my Hilbert basis, okay, and then we'll show that is the case. let H be the set of integral vectors defined as follows. Okay, so that will become our candidate Hilbert basis. Okay, if A is in H, if and only if A is element of C, it must be inside this cone. A is non-zero, and A is not sum of any of the other two non-zero integral vectors in C. Okay, so you just some sense they are the smallest vectors which cannot be represented as a sum of any other vectors. Okay, and you collect those. Okay, so in our case, you have these in this cone. We turn out to be these three vectors. Okay, they cannot represent as a sum of anybody else. For example, this vector, this is just twice of this guy. Okay, only these three vectors cannot be written as a sum of any two other vectors. Okay, we'll claim that this is going to be our Hilbert basis. First, we can see that anybody who is in Hilbert basis must contain these vectors, because these vectors cannot be represented by as a integral combination of any other vectors. So if they are not in your set, how do you represent them? Now, we need to show that this itself is sufficient to be Hilbert basis. You don't need any more vectors. How do we do that? We just take a vector B. Okay? Vector B doesn't have to be inside the cone. It's a sum vector B. And it has this property that if you take a dot product with any vector in this cone, it gives you positive number. Okay, assuming X is B is not an origin. Okay, so choose vector C such that C is not a non-negative integral combination of H. You just pick C somewhere in the cone and say this is non-negative linear combination of my H, and I'm going to show there is a contradiction. Okay, and let BC be smallest. Pick the C which produces BC smallest. Okay, so pictorially this looks like this. We had this cone which is a red one, and we had these three vectors which are belonging to H. Okay, three blue vectors. We chose B, which is this this vector. You can see that it makes an acute angle with every vector inside this cone, so therefore its dot products are positive. Okay, since it's not is a part of H, it can be represented by the sum of some two integral vectors C1, C2. Okay, that's the definition of H. Something is not in H, then they should be able to sum of two vectors. Okay, now I take a dot product of C1 and with B. Okay, if you can see the dot product of with B, you can see that since BC1 must be smaller than BC, and BC2 must be smaller than BC, and C1 and C2 are non-negative integral combination of H. Since I have chosen BC to be the smallest, so therefore C1 and C2 must be non-negative integral combination of H. Therefore C is a non-negative integral combination of H. Okay? Because C1 and C2 can be represented, then you can just add them and then you get C. So it should be possible, and therefore you have a contradiction, and this gives us a uniqueness of Hilbert basis. So Hilbert basis is a fundamental concept using which we understand integral cones and proving that that our proof system is complete. I'm not going to go any further in this lecture, but there are more slides continuing onward where you can see the complete proof.